Okay, now let's talk about conservation of charge. This is one of the laws of physics that you will come across. We have lots of laws of physics and chemistry that you need to learn. This is indeed a law that you need to learn like a parrot from your list of definitions. And this is what leads to us doing calculations. Usually a law leads to calculations. So the law of conservation of charge tells you that the net charge in an isolated system remains constant during any physical process. So what does this mean? Look here, net charge. Remember I said to you, the net charge is like the overall charge or the final charge. And if there's no net charge, then it means everything's neutral. So the net charge, whatever charge you've got existing in an isolated system, so in physics we like isolated systems that are not in contact with anything else. Remember, all of our things are in insulated stands. This is one of the ways we're making an isolated system. So the net charge in an isolated system remains constant. It's not going to change during any physical process. And a physical process is like touching or something like that. With electrostatics, the physical process is usually touching. So this law leads to this equation. The sum of the charges in a system before contact is equal to the sum of the charges in the system after the contact. Okay? So this charge ends up being the charge on objects. You have Q1 and Q2. These are the two objects. And the sum, to find the sum, you add. So the sum of the charges in the system before contact is equal to the sum of the charges in the system after contact. So if we have two charged objects, Q1 and Q2, and they touch, the final charge is going to be Q1 plus Q2 divided by 2. Okay? The second thing that goes with this is the principle of quantification of charge. This is based on all charge comes from electrons. So every charge in the universe consists of integer multiples of the electron charge. Now, we cannot get half an electron, hence this word, integer multiples. So the charge on an object measured in coulombs is equal to the charge on an electron. This is this Q sub E, also measured in coulombs. Remember, it's that tiny number. So the charge of the object is equal to the charge on an electron multiplied by any whole number in the universe. So if you've got one electron, you've got 1,6 times 10 to the minus 19 negative charge. If you've got two electrons, you've got 2 times 1.6 times 10 to the 19 coulombs negative charge. If you've got 100, it's 100 times 1,6 times 10 to the minus 19. So sometimes this is written as N equals Q over E, or otherwise it's written as Q equals NQE. Okay, so if you need to know these numbers, they on the exam paper, N equals Q over E and Q equals Q1 plus Q2 over 2. So over here, here's your E, the charge on an electron, and here's its value with its unit. Okay, it is your job to remember that Q is the charge on the object in coulombs, N is the number of electrons, and E is the charge on a single electron. So here this means charge equals charge 1 plus charge 2 divided by 2. And we use this for when objects touch each other. How do we know that that N is an integer multiple? So there's this guy, Robert Millikan. He was very interested in charges and measuring charges and everything. So he won a Nobel Prize for his work on this. It's quite a cunning plan. He had a little bottle of oil here with a squishy thing, and he squishied the oil into a very, very fine spray. So it was tiny little drops. And then we had these two plates here. This metal plate is charged positive, and this metal plate is charged negative, like you connect them to a battery or something to give them a charge. And then he charged the oil droplets between these two plates. He put an X-ray in because X-rays are special radiation with a lot of energy, and they can put the charge on the oil droplet. These really, really fine oil droplets. And then he sat here with his eye on this little telescope, and he watched in here. So what happens is here comes in the oil, okay, and the oil goes through the drop here, and then the moment it's charged, is going to want to be attracted to a plate, either a positive plate or a negative plate, depending on which charge it is. And he had these plates connected to something that could alter their value. And he could get these little electrons to go, these little oil drops, to sit stationary where he's watching them with a telescope observer. He could get them to sit stationary between the plates by fiddling with a charge on these plates. And when he did this, when he worked out how much charge he needed on each of these two plates that he was using electricity with something to change the current on it, when he found all of these always had multiples of the same number, and that's when he discovered it was the charge on an electron. It's a very cunning experiment. Okay, so how do we use this knowledge? It says to you, for example, how many electrons were transferred if an object has a charge of 7.15 times 10 to the negative 9 coulombs? So here, this value in coulombs is Q, our charge. We know the charge on an electron because we got it off the data sheet. We got this formula off the data sheet. And this is how we find N. We put Q, look here, Q, we put it in the formula. We put this from our data sheet in the formula. And then N is our unknown, and we perform algebra. Yes, to get N by itself, we must take this number and divide it on that side, or if you prefer, divide both sides by 1.6 times 10 to the minus 19. And here he ends up with a number 4.7 times 10 to the power of 10 electrons. There's one thing I want to bring up here. We often get microcoulombs and nanocoulombs. This relates to King Henry. You need to remember your King Henry. If you get a microcoulomb, it's 1 times 10 to the minus 6 coulombs. If you get a nanocoulomb, a 1 NC, it's 1 times 10 to the negative 9 coulombs. And now let's have a look. What do we use electrostatics for? We use it in things like spray painting cars, photocopiers, fingerprinting, and for reducing pollution in electrostatic precipitators in chimneys. So how does it work in spray painting cars? You've got this paint gun, and this is going to a tank of paint, and they put a tiny little current into the nozzle here, and then as the paint particles fly past, they get a tiny little charge, and then meanwhile somebody's put another electrical lead on the car. So this becomes negative, the car is positive, and then the opposite charges attract, and boom, the paint sticks to the car without flying all around the room and being wasted, and then it sticks harder to the car as well because of the charges attracting. Photocopiers work on a similar system with the image gets charged, and there's actually powder in photocopiers that gets the charge and then sticks to the paper. Fingerprinting as well, the dust is attracted to the very fine powder dust. There's like things with the fat in your fingers where you left your fingerprints. There's fatty bits and non-fatty bits that it sticks to because there's a charge on fats. And then let's look at the electrostatic precipitator. You have a giant chimney and you put steel plates in the chimney, okay? And then obviously whatever you're doing down the bottom here is making little soot particles, little dirt particles. And then you charge the soot on a grate as it goes past. You see these thin metal rods? They make like a grate, these blue ones. And then as the soot goes past, it gets a charge. And over here are some other metal plates with the opposite charge further away. And then as the soot is passing these plates, it gets stuck on the plates and the rest of the gas passes out. And then every so often you give these plates a good shake and you collect the soot off them. And that's how it stops. That's how electrostatic precipitators in chimneys work, and they reduce pollution by stopping little horrible particles going out into the atmosphere. And then there was your homework. I will try to check through your homework and maybe give you an example of how your homework is done. And that's all for now.